Okie doke. So today we're going to talk about star formation. And we're going to talk about star formation in a galactic context. Um, yeah, so really we'll talk about the reason that we want to talk about star formation is we want to understand galaxies. So we want to understand why galaxies are the colors that they are. And so to do so, we need to understand the stellar population. And we need to understand, so since stars form and then die basically immediately, at least from a galaxy's point of view, they form and then die basically immediately. We need to understand the formation as well as just the stellar population, because the stellar population is dynamic. I'm giving the colloquium on Thursday, so if you want to see more details about this and the stuff that I'm actually doing research-wise, I'll be talking about this on Thursday, and I'll present basically nothing there's basically no overlap between my talk on Thursday and what I'm talking about here, aside from it's about star formation. 3:45 in UPL 101. There's cookies at 3:15. So if you want,
I've been trying to go to the colloquium, any of them. Like,
that's a good plan.
For the last 2 semesters, and I've never been able. Like I always either forget or I'm busy. So I'm like, now is like the perfect time because I think last semester I had a class at that time, so it didn't work out at all. This semester I'm like free. I just never managed to go.
They're good. The last couple have been good. There have been some good ones so far.
Hell yeah.
Let's see. So there was a reading up that I haven't gone over yet, and I still haven't gone over it. So if there's a question that you had asked in your reading sections that I get to the bit and you're like, oh, I don't understand that, just holler. I'll go through the questions carefully on Thursday. Did I post? Can I see Canvas from my phone? I don't know if I ever done that.
You posted a bunch of readings.
I did. Did I post the chapter 4? And is it due? I just want to double check that it's due
It's next Monday.
next Monday. Okay. So start chapter 4 next Monday. We'll start cosmology. I don't need you to go away. We'll start cosmology next week. Where were we? So we were talking about star forming clouds. So this is M42, which you can go see. This is a really nice one. So I start most of my talks with M42 because you can just go outside and look at it, and it's right there. And if you have a pair of cheap binoculars, you can see that it looks like this. You can see all the stars that are going on. So this is a stellar nursery. So this is a star forming region that's large. It's a couple thousand solar masses, and is actively forming stars. Now we know from the dynamics of this thing that its free fall time is about 3 million years. And we know from the stellar populations that the oldest stars in here are about 10 million years old. I haven't gone into the how to age a star, but that's possible. So the question is, why is this object still here? And the answer is turbulence. And I'm not actually going to talk about the turbulence at all. For a long time, people thought magnetic fields did it, that magnetic fields were holding up these clouds. But now that we measured them a little bit better, that's pretty much dead as an idea. Which is funny because I started doing star formation. I started studying star formation about 20 years ago. And this debate of magnetic fields versus turbulence was raging pretty hard. So during my tenure and I started studying the magnetic fields in star forming clouds, and then as time went on, I realized, what the magnetic fields actually are just along for the ride. They change some things, but they're not the dominant mechanism that holds this cloud up. It would be cool if there was a big magnetic field that held this cloud up, but it's not actually capable of doing that. Here's Taurus, which I like because it's a low mass star forming region. It's not forming any massive stars, which is weird. Here's Serpens is another star forming region. W33, and I put up some new ones. Oh, I talked about the Ghoul Belt, which is cool. Got some new slides, new stuff. This is they call this the Cliffs of Creation. This is a JWST image. of a molecular cloud. So this is an object that's within our galaxy, and is an active source of star formation. Um, you can see a bunch of cool stuff in this, and this is like there's really an enormous number of cool things in this image. Uh, a lot of them are, so one of the things that you can see is, you see how it's really dark here, but there's this kind of haze coming off the cloud? That's photoevaporation of the cloud. So there's a really large cluster of O and B stars just to the north of this image. And the UV photons from those O and B stars are destroying this cloud and driving shock waves through this cloud and doing all kinds of violence. So they're evaporating off the surface, and the pressure is driving shocks through the cloud, and those shocks form stars. So in these dense regions that are just getting beat on by the radiation pressure, you can see here we've got a young stellar object that's just formed here. Here's another one. So now most of the time when I show you a JWST image, the things with the diffraction spikes are in our galaxy and not part of the image that you're looking at, because most of the time what we look at are galaxies that are far away, and those don't give you diffraction spikes. But this is a pretty close by object, so you get diffraction spikes from stars that are related to this object. So this is a protostar. I think this is actually embedded. I think these guys are actually embedded in this cloud and not foreground objects. So you get these little baby stars. You get these knots of stuff. I was going to... So there's objects in the other one that are really cool. I'm not going to talk about them because I don't have that image. This one is called the Pillars of Creation, which maybe you've seen before. So this is what it looks like in the optical if you're not Hubble. But if you're Hubble, this is what it looks like in the optical. And you can integrate for a long time, and you've got great big eyes. If you look at it with JWST, you can see a lot more structure because JWST is a more sensitive instrument, and it sees in the infrared. So one of the cool bits you can see are these red things here. Yeah.
Until now, I thought those two images were the same thing, like last light and this light. Are they the same thing, or do they just look alike?
Oh no, this is a different object than this.
Oh, okay.
It's a different part of the galaxy.
Okay.
There are bunches of these. This is called the Cliffs of Creation, and I forget what its NGC number is. I should have written that down. But it's a different region than this. And there's another one even that I just found. This came out mid-December. This is another star forming region. You can see these embedded sources. These are objects that are deep in this cloud and still forming. And I love this one because it feels very cloudy. It feels very, very murky. So what are these objects? So this is M74. It looks kind of bad on this. Here, let's write M74 just so that I remember. This is M74. It's a galaxy. You can look at it in Hubble, JWST, and it looks like this, which, man, this kind of stresses me out. Like, it gives me the jeebies. This is what it's supposed to look like. It's all spectral and, like, eaten away. Because you're looking at different stuff. You're seeing the dust mostly. So this is a lot of dust and colder stuff. So this cloud, this guy here, or this guy here, these molecular clouds, they're like this little bit here. Like just this little chunk. They're real small relative to the galaxy. They're large relative to a star. Yeah.
Sorry, going back to like 3 slides ago, I guess. The one before that. You pointed at like the little red objects there. What were those?
Yeah, these are baby stars.
Okay.
So these are young stars that are just forming, and they're bright red because they're super dusty and haven't really started forming everything else. They probably haven't started burning hydrogen yet, but I'm not sure.
Nice.
So these little red guys are, you can't see them in this image. There, let's see, right here, you can't see them. There's a red thing at the end of this one too that you can't really see. See these red guys here. So they're little stars, and you can see this shock right here from the flow driving driving a shock region. All of these things are shocks. So have you ever gone on a boat? So if you've stood at the front of a boat, you can see that the wave of the boat's traveling faster than the surface gravity waves on the water. So if you just put your hand in water, a ripple goes out. That's the surface gravity wave. Boats travel faster than that, so you get a shock in the wave system that's shaped like the bow of the ship. So your ship is shaped like that, for all intents and purposes. A ship is a line. As it's traveling up this way, you get a shock like this. It's called the bow shock, or the bow wave. The bow is the front of the boat, and the stern is the back, and port is one side and starboard is the other, and I have no idea which of these is which. And you can tell, so why is it curved like this? Because the wave is going out at the speed of the surface gravity waves, but the boat is going up at the speed of the boat. So the angle here is going to be the speed of the gravity wave this way and the speed of the boat this way. So you can use geometry and this angle that the bow shock wave makes to find the speed of the boat. Oh, I didn't record any of that. That's okay. So all of these things, you can sort out what the flow speed is doing, because these are all basically bow shocks. They're not completely bow shocks because they're also being destroyed by the photons. So it's more complicated than this. It's more complicated than a boat by a little bit. But okay, that's what star forming clouds look like. So let's get to the important questions. The two important questions in star formation, which I'm not actually going to answer. I'm just going to say these are the important questions, because the answers are kind of, well, for one of them, I don't like any of the answers. And for the other one, I'll talk about it a little bit. So the first question is, how big do they get? And that is, the question is really, what is the initial mass function? How do you get the initial mass function from a star-forming cloud? And second, how fast do they form? And that has to do with the star formation rate. Both of these things are important if I want to understand, for instance, the abundance of uranium in the universe. So if I want to understand the abundance of uranium in the universe, what do I need? I need the number of stars that can produce uranium. So that involves the mass distribution. And I need to know how often they explode, and that involves the star formation rate. So these are the two questions that underpin why star formation is important as a field to study. So the IMF, I'll talk about what they are. Oh, this is kind of a cartoon. This is an older slide, but this is one of the pillars. They form all these dense knots. This is called a cloud. Inside this object is a core, and these things fragment into little baby stars and then eventually spit out jets. I'm not going to talk too much about the jets today. So the IMF is the distribution of star masses at the birth of the stars. So how do you get the IMF? How do you measure that? So measuring the IMF is actually very difficult because of the I and also because of the M. And F just means function, so that just means we're writing something down. So it's just hard to do. So how do you actually measure this? So the first thing that you measure is the light function. This is the distribution of light coming off your stars. So you need basically a spectrum. Then you use stellar evolution and spectra to turn this into a mass function, a present day mass function. So you got to turn the light into the mass of all the stars. That's pretty tricky too. You got to understand how the mass distribution works, but it's relatively straightforward. It's a process you go through, but it's tricky. 3, you've got to use evolution codes like MESA. or other stellar evolution codes to take these stars and drive them backwards in time. So you don't have to do this every time. Somebody did this and you say, okay, I've got a 5 solar mass star and I think it's 2 million years old. What was its initial mass? So we use stellar evolution understanding to run things backwards in time to get the initial mass function. So you got to get the present day mass, you got to get the light function and then the present day mass function, and then you can get the initial mass function. All of this is really messy and tricky to do. So the initial mass function is actually a really error-prone measurement. So what is it? So we see experimentally that it is a power law with a slope of, can't click on that, minus 2.35. But that might not be universal. So that's what you get if you integrate over the whole galaxy. So you measure the initial mass function for basically everything in the Milky Way, and you get minus 2.35. If you look at other galaxies, you get slightly different distributions. So if you look at, for instance, the Small Magellanic Cloud, the Small Magellanic Cloud has less metal in general than the Milky Way, which changes the star formation. Why? Why does metal change the star formation? Because metal is a coolant. So what does cooling do? You remember talking about the gene's mass. Gene's mass is proportional to the temperature, right? To the 3 halves. The gene's mass, okay, so the gene's length is the sound speed over the free fall time, square root of g rho. The gene's mass is that cubed, but this is equal to, the sound speed is the square root of the temperature. The temperature, the sound speed squared is the temperature, so the sound speed is just the square root of the temperature. So the gene's mass is going to go like the temperature over g to the 3 halves, rho to the minus 1 half. I get an extra rho when I get in here, so I cube this and then multiply by rho, right? I get 3 halves for everybody except this guy, which only gets 1 half. Okay, so temperature to the 3 halves. So that's a strong power of temperature. So when the temperature goes up, so does the mass of the cloud. Or so when the temperature goes up, the mass of the cloud doesn't change, because that doesn't care. But the mass of stars that it will form changes. And this depends on, so temperature and metallicity are related because metals cool the gas. So if you can't cool the gas very well, that means your metals are low, then you're going to have a different mass function. Possibly. We're not really sure. So this is the tip end of a very deep, big iceberg of research. So we're going to go with the mass distribution is minus 2.35 for basically everything. But in some scenarios, you might have a top-heavy mass function that has a steeper slope because you've got bigger masses because you have less metals. Or if you have something that can cool really aggressively, you might have a bottom-heavy slope that's steeper because you have more little stuff because you can't form the big stuff. Does that make sense? Everybody all right? You got a confused look on your face. Everybody good? So the initial mass function is an important thing that you got to measure. You can predict it, but really not very well. So the predictions aren't great. There are a couple of things that you can predict. There's a couple of things, but we don't really understand very well this mass function. We understand it basically well, though. Why? Because it takes more volume to make a bigger star. So there's going to be fewer of them by a lot because that volume goes up pretty fast. I mean, it's going to be at least proportional to the mass. So, way fewer massive stars than low mass stars. Does anybody have any questions about the star formation rate or the IMF? So this gets folded into a lot of calculations. So like if I told you that an O star produces 1% of its mass gets turned into iron, and then we can sort out how much iron gets produced every year by saying we're going to multiply by if we've got the yield, which is say iron per solar mass of the star. This is iron produced per solar mass of the star. Then we get the iron, the total iron production by just multiplying by. This is a function of mass. We gotta integrate the yield, which is a function of mass, times the IMF to get the total amount of mass. Does that make sense? So this is just a distribution, so we just multiply the yield times how much of each one of those masses I get, and I can get the total mass. If I want to get the total rate, then I can multiply this by the star formation rate, and that will give me the rate of iron production. All right, so what is the star formation rate? So that's the mass. Then we need to talk about the star formation rate. Let's go talk about measurements. Okay, so how do you measure the star formation rate? You measure the star formation rate. Measure the IMF. Measuring the star formation rate is actually easy to do, but the math is hard. The measurement is easy. The measurement, you just measure the luminosity in H alpha, and then you multiply by some number, and it gives you the star formation rate. Where's that number come from? So, massive stars give off ionizing photons. So we count all the massive stars. Okay, this is actually what we're measuring, but let's just in our head say I got a stellar population. I'm going to count the number of massive stars. So this is just an integral over the IMF. So we just integrate from, say, 8 or so solar masses to infinity over the IMF. And that gives me the total number of massive stars. I compute the UV photons per mass. And I can get that. So the number of UV photons is going to be, again, the same integral, but we're going to include the UV photons per mass times the IMF. We integrate over mass. So the number of UV photons is just going to be an integral over the IMF times how many UV photons I get for each star. Then I sort out how fast. Then I have a couple of things that I can do. This is the important bit. How many ionizing photons do I get? This is going to look like, essentially, so it's going to be integral over UV photons per mass, which is a function of mass, times the IMF, dm. But that's really, we can just think about this as the mass in stars times the average photon per mass, and I get a total number of UV photons. The thing that I'm trying to get is the total number of stars. So in my thought experiment, I already know my population of stars, so I'm just going to count everything. With a telescope, I'm going to measure a bunch of photons, and then I want to back out the mass. So here's where the mass shows up. The number of UV photons is the mass times the number of photons you get. The mass in massive stars times the number of photons per massive star. This is actually an integral. I'm just writing it as a product to save effort. So then I need to think, am I going to do my measurement in the UV or in the infrared or in the optical? So there are 3 different ways that I can make this measurement. And they all depend on, I start off with UV photons, and then those UV photons do stuff. So what do the UV photons do? They ionize hydrogen, and then the hydrogen recombines and gives you H alpha along the way. What's H alpha? Do you guys remember? One of the ground state transitions. It's the 3 to 2 ground state transition in hydrogen. It's a visible line, it's red. So in the optical, we measure H alpha, which is UV photons ionize hydrogen, and the recombination rate gives you the number of H alpha photons per UV photon per time. Because if I have one UV photon, it will ionize a hydrogen, which eventually will then recombine and give you an H alpha photon, which doesn't go at the same rate necessarily. So we need to know the recombination rate to H alpha from the UV photons. We can do this in the infrared by saying that UV photons heat dust. So then we get the infrared flux, which we can sort out from the UV flux. This is harder to do. The easiest thing to do is measure the UV photons directly. So if I can measure the UV light from a stellar population, I know how the star works, so I know the UV per mass, and I know what the initial mass function is, so I can get out what the mass is by just looking at the UV UV light that I'm getting from those stars. Does that make sense? But it's tricky to do. Why is UV tricky to do?
Because it's about the size of the dust is going to affect it?
Shorter than, by a lot. So a UV photon is substantially shorter than the dust that is in the way. So you can't really see the UV very well because there's all this dust in the way. And there's this stupid atmosphere in the way, which is really opaque to UV, despite what my skin cancer rates might say. There's plenty of UV from my Northern European complexion, but the atmosphere really does block a lot of UV photons, which is why you got to wear a spacesuit above the atmosphere. Probably not the only reason. So UV photons don't travel very far before they run into something. So this is a great way to measure the star formation rate, is with UV photons, but it's hard to do. Infrared is another good way to measure the star formation rate, but the conversion from UV to infrared is a little dodgy because it's kind of a messy process, because the infrared is produced by these big dust grains, and their distribution is not well constrained and stuff. Optical is really one of the nicest ways to do it because the optical photons go through everything. We have a bunch of optical telescopes, so what we do is we just say that the star formation rate is the luminosity in H alpha times this number, which is on the next slide. There you go. 1.26 times 10 to the 41 ergs per second. Sorry, you got to divide. You multiply by the reciprocal of this number. I forgot how I wrote it here. So you take the Lyman alpha flux. That's how many H alpha, or the H alpha flux. So that's how many H alpha photons you get. From that, you get how many UV photons you needed to make that. From that, you get how many massive stars you needed to make that many UV photons. And then you have the mass in UV stars, which is not a rate. It's a mass. I want mass per time. What's the obvious time scale to use? So this gives me a mass. What's the time? What's the only time scale in this situation? Years, sure, but years are the same for everybody. What's the physical thing that's going to set the time? When does this star formation end?
Lifespan.
Yeah. What's short?
Massive star lifespan.
Yeah. Massive star lifespans are short. Okay, put a pin in that. What's a derivative? Let's back up a second. I don't. I'm going to leave that up because I think I want it. What's a derivative? df dx is the limit as x goes to 0. Let's call this h. As h goes to 0 of f of x plus h minus f of x over h. So a derivative is just a fraction of a thing changing over another thing changing, but the thing on the bottom gets really small, right? So the thing on the bottom has to be small for a derivative to really make sense. Massive star lifetimes are small. So we do all of this to get the mass in massive stars, and then we divide by the lifetime of the massive stars, and then we have a star formation rate. Doesn't really matter if we're in the middle. Doesn't really matter if we're integrating something that's long compared to only 1 million years. It's only 1 million years. Really isn't very long. So massive stars don't last very long. So when we're measuring the star formation rate, we're just going to do all of this complicated business, and then we'll divide by the main sequence lifetime of the stars to get the answer. Does that make sense? Okay, so when you get to the homework, this is the slide that you're looking for. How to measure the star formation rate. The slides are here. The number that you're looking for is either this one or this one, depending on how I give you the problem and which problem I actually assign. So if I'm using an optical telescope, then I'm going to measure h alpha because that's an optical line. Then I use the top formula. If I'm using an infrared telescope, then I'll measure in the infrared, and I use the bottom line because we're measuring the dust heat. Does that make sense? Okay, so that's how you measure it. So now let's talk about it and what it means. So we're going to first talk about it at the molecular cloud level. So what is the star formation rate if I'm a molecular cloud? And then I'll talk about what is the star formation rate if I'm a galaxy. And then I'll talk about the star formation rate if I'm the universe. So we'll just get bigger and bigger in scale, and the story is always about the same, not very fast. There are lots of ways to stop star formation. It's kind of like a lot of processes that are much easier to kill than make. So on one hand, stars are really ready to form. Gravity only goes in one direction. There's only one sign of gravity. So stars are inevitable. They have to form because eventually gravity wins. Gravity always wins. Tom York taught us that in the 90s. But it still doesn't go very fast, so that's kind of strange. So let's look at that. There are many places between a cluster of galaxies where a galaxy lives and an individual molecular cloud where the processes are happening. There are many stages along the way where you can kill star formation and make a dead galaxy. We'll talk about normal galaxies for the most part and spiral galaxies for now. So what does the star formation look like from a molecular cloud point of view? So what we actually want to measure is not the star formation rate, because that is an extrinsic property. You guys have talked about extrinsic. Oh, you guys haven't had thermo yet, have you? You guys talked about extrinsic and intrinsic properties. Not a ton. Let's do that for a second. Let's take a quick detour. So an intrinsic property does not depend on how much stuff you have. An intrinsic property is something that doesn't depend on the amount of stuff you have. So if I double the stuff, I double this, whatever this is. So this is something like temperature, density, pressure, color, flavor. If you're talking about chocolate. But temperature, density, color, those are the things. Those are the typical intrinsic properties. Actually, maybe color isn't necessarily intrinsic. We'll just stick with rho, P, and T for now. Also, the star formation rate per free fall time, which I'll talk about that in a second. This is where I'm going. An intrinsic property doesn't depend on the amount. An intrinsic property doesn't depend on the size of the system. An extrinsic property does depend on the size of the system. So this is like the mass, the total luminosity, the kinetic energy, the gravitational energy. That depends on more than just the mass. I can increase the gravitational energy of something by switching it. But it's an extrinsic property. If I have double the things, I double the energy. So extrinsic properties are like mass and luminosity and kinetic energy and stuff. So depends on the stuff. Also in this is the star formation rate. The total star formation rate. It turns out some of these are not linear properties. They don't depend linearly on the amount of stuff. The mass does. If I have two galaxies of both M1, then they have a collective mass of 2M1. But the gravitational binding energy, depending on how close they are, might be quite a lot bigger. The star formation rate is a weakly dependent property of the mass of the galaxy. So it goes up with galaxy mass, maybe not the way you expect. So intrinsic and extrinsic properties are things that you'll deal with when you get to thermodynamics, and you're talking about like pressure or mass, those kind of things. So thermodynamics typically deals mostly with the intrinsic properties. And so since we've got a universe that's infinite, any of the extrinsic quantities that we might come up with are also infinite. So as an astronomer, we deal with intrinsic properties most often, or quite often, because they're really a more process-independent, a more system-independent way to think about things. So the star formation rate per freefall time is a better way to describe the star formation rate It's kind of hilarious to watch a video of yourself doing something while you're trying to do it, but not actually looking at what you're doing. So the star formation rate per freefall time is equal to the star formation rate divided by the mass of the cloud divided by its freefall time. Why do I want that? This is the intrinsic quantity that you can make. So if I double the size of the cloud, I double the star formation rate, in principle. I double the mass, I don't change the freefall time. So the doubling of the mass cancels out, so I get the same star formation rate per freefall time. Does this make sense? So what I want is for the star formation rate just to be the mass of the cloud over the freefall time, right? The freefall time is just how fast something should collapse if there's nothing going on. This assumes a spherical universe, which we don't have, and that's really part of the problem. Geometry is actually part of the problem why this process is slow. So what we want to see is the mass over the freefall time. That should be how fast stars go. But this is actually a lot bigger than the actual star formation rate. So we get a number that's less than 1. So here we have a measurement from several local clouds. Now, I told you about measuring star formation rate with UV and infrared and optical. This is using radio, similar process. But we have, on the horizontal axis of this plot, we have the density of the cloud, and on the vertical axis we have the specific star formation rate. And you can see that this is around 1%. So here's 1% right here. Here's 10% right here. And this band is predictions from this star formation model that I'm actually going to spend most of the time on. I'm going to on Thursday I'll very briefly present this model and then spend the rest of the time unraveling it and showing you why it doesn't actually work, but I still love it as a model because it's a really good model for the bulk. It just, in detail, it doesn't work. So we'll talk about this model on Thursday during my colloquium. But so this is carbon monoxide measurements of close things. This is infrared dark clouds, which are dark clouds that you can see that you can't see in the infrared because they're also opaque in the infrared, you can tell that they have high column density in the infrared. Other clouds at higher density. So this is a higher density tracer of stuff of the star formation. It's in the molecular line. So we have all of these different measurements from different molecular clouds. The Orion Nebula is up here. That all show that the star formation rate, if you're a molecular cloud, is slow. So yeah, so we're looking at a percent of what you should expect. If we look at a galaxy scale, then the way that people think about star formation rate at the galaxy scale is through the Schmidt law, or the Kennicutt-Schmidt law. Kennicutt's still alive and very active, and I think that he doesn't really like calling it the Kennicutt-Schmidt law because it's his name. Every time I've seen him give a talk, he always calls it the Schmidt law. Go figure. But anyway, so this law, we've talked about this a little bit already, but since I'm here, I'm going to talk about it again. So on the vertical axis, we have the star formation rate per surface area. Now, this is not specific anymore. We deal with a specific star formation rate when we're looking at molecular clouds. Now we're looking at the mass of the galaxy. The mass of the galaxy probably shouldn't matter for star forming regions because just like, I live in a neighborhood, it's my molecular cloud. If I have a bigger city, there's another neighborhood with more but the total specific star formation rate shouldn't care about the size of the galaxy because that's small stuff. It turns out it does, but so when we're dealing with galactic star formation, we use slightly different units. Here we use these units here, which are in solar masses per year per square kiloparsec. And here you get values of a few percent to a couple thousand. So you can have a couple thousand solar masses per year per square kiloparsec. That's a buttload of star formation. So a square kiloparsec is a good size chunk of the disk. But 1,000 solar masses a year is a lot of stars. That's a lot of star formation. And on the horizontal axis, we have the surface density of gas. So this is in solar masses per square parsec. Instead of kiloparsec, it's easier to deal with parsecs. The numbers are like 1 if you do it that way. And so what do we see? We see that the surface area star formation rate is proportional to the surface area of the gas surface density to this power that's like 1.4. So we can understand that a little bit by looking at instead the gas surface density divided by the dynamical time. So again, we need a mass and a time. So the relevant time scale, if you're a galaxy, is one orbit of the galaxy. And that's just proportional to the size of the galaxy, right? So what this says, so if you divide the gas surface density by the dynamical time and compare it to the star formation rate, what I expect is as a cloud goes around the galaxy, most of it's going to turn into stars. Turns out only a small percent of it turns into stars, and that's what this plot shows. If you can look at the details of this plot, that's what I got this square here for. So if I look at a star formation, a predicted star formation rate of 10 on my line, I get an actual star formation rate of like 0.03. You see that? This is a logarithmic axis, so -2 here is 10 to the -2, so this is 0.01. So we're a little bit above that, so we're like 0.03. So again, we're at like a couple percent of my cloud of gas turns into stars as it goes around the galaxy, which isn't very efficient. It takes a bunch of orbits for a cloud to turn all its crap into stars. They don't actually live that long because they'll get destroyed by the motion in the galaxy. The motion in the galaxy is like a blender. And this depends on environment. So here, this is another great plot. This is from Exgal et al., 2008, which is one of the more highly cited papers in star formation now. I went to a conference on star formation just after this paper came out, and basically every talk put this plot up because everybody was like, check this out. So what this shows is, again, the specific surface density per unit area, so in solar masses per year per square kiloparsec, versus now the total gas column density, which is both the H1 and the molecular hydrogen, which Kennicott skipped the molecular hydrogen because it's hard to do. You have to measure the molecular hydrogen with proxies, and usually that's in the radio. Molecular hydrogen's a headache. So they got the molecular hydrogen and the H1. H1's easy to see because hydrogen, the ground state transitions of hydrogen are all in the optical. So neutral hydrogen, H1, is easy to see. It's bright. It glows. H2 is very difficult to see because it gets cold and it gets opaque because it doesn't give off any light. So you got to fake it for the hydrogen. So what do we see? This is now the total solar masses per square parsec versus the star formation rate. And so this is what's in this line. So this is a whole bunch of different kinds of galaxies. And each of these lines is a constant depletion time, or a constant depletion fraction at 10 to the 8 years. So after 10 to the 8 years, this is 100% efficiency. So that means all of this stuff turned into stars. So all of this turned into that. All my surface gas density turned into stars. It has to be the gas density, not the star density, because the stars don't turn into stars. The gas turns into stars. So here we're turning all of this gas here into stars up here with 100% efficiency. You see, nothing is at 100% efficiency. Every one of these things takes more than a gig year to form all its stars. Normal galaxies are down around like 5 to 10% of the efficient. And then low star bursting galaxies don't form stars very much at all. So that's really kind of surprising. Does anybody have any questions about this plot? Galaxies are bad at forming stars. That's what this plot tells us. Except for a couple of rare dudes. And these starburst galaxies are usually collisions of galaxies. When you smash two galaxies into each other, it turns out the density gets really high, and you get a bunch of star formation. More quiescent galaxies don't do that. Okay, let's talk. So this is what star formation looks like if you're a galaxy. The last bit I want to talk about is star formation if you're the universe. So this is now the star formation volume density in solar masses per year per cubic megaparsec. So you can tell what kind of scale we're dealing with by the units. So when I don't have any parsecs or anything at all, I'm looking at molecular clouds. When we've gotten rid of the mass entirely, we're looking at molecular clouds. If I'm looking at things per unit kiloparsec, then that's a galaxy. Because a galaxy is like a kiloparsec, right? The Milky Way is like, what's the radius of the Milky Way? It's like 40 kiloparsecs. If I'm looking at the entire universe, then we want to do things in terms of cubic megaparsecs. So this is the star formation rate per solar mass, in solar masses per year per cubic megaparsec, versus Z, which is redshift. We'll learn more details about what redshift means in next week. But basically, it is a measure of the size of the universe. It's the inverse of the size of the universe. So 1 over 1 plus Z is the size of the universe. So 0 is the universe with the size of 1. Makes sense? There, let me write this down. A equals 1 over 1 plus Z, and it's the size of the universe. So at a redshift of 1, how big was the universe? 1/2. At a redshift of 0, this is 0 and you get a 1. At a redshift of 1, you get a half, because the universe is half the size of it that it is now. At a redshift of 11, it's a 12th of the size. At a redshift of bigger than that, you can get the 1. So, a redshift of like 2, when the universe was about a third of its current size, that's what we call cosmic noon, because this is where the star formation rate in the universe seems to peak. And then it goes down after that. So what it looks like is the star formation rate kind of ramps up slowly over time and peaks at about a redshift of 2. Around a redshift of 2 is when the acceleration from the universe starts to expand, and the density of the universe is pretty low. So by the time you get to now, the density of the universe is relatively low and it's expanding pretty fast. Yeah.
Is A the scale factor?
Yeah. Yeah, so this is the size of the universe. So you can think about this as the size of the universe relative to today. Those are the units that I care about. Yeah.
Will there be a point in time where there's like no star formation?
Yeah, probably. After everything dies, and the heat death. So once the universe is expanding really fast, then nothing can see anything anymore. A galaxy itself has largely decoupled from the Hubble flow. So I'm not expanding. You're not expanding. The galaxy is not expanding, but the distance between this galaxy and other galaxies is expanding. So once the Milky Way collides with Andromeda, it'll make another probably spiral galaxy. That'll have a bunch of star formation. Eventually all that star formation will be eaten up and made into K stars that live forever. Then you'll just have a galaxy that's just made out of K stars that are going to live, for forever. They'll all just be white dwarfs that are slowly cooling. Dissipation in the galaxy will slowly drain everything into the black hole at the center. So the star formation will stop just because you're going to run out of gas and everything's going to be too hot. Then it'll all get drained into the black hole in the center, and then eventually the black hole will evaporate, and then there's nothing left. And that's how the universe ends.
Do a lot of galaxies end in that way, where the black hole in the center eventually swallows?
We haven't ever seen that happen. So that's like 5 times the current age of the universe into the future when that starts to happen. So that's a really long
Another
process.
era.
Yeah, it's a totally other era. Yeah.
You said the black hole evaporates?
Yeah.
What do you mean by that?
A black hole will slowly evaporate by Hawking
Oh,
radiation.
right, okay, yes.
So when a black hole evaporates, so the way Hawking radiation. Let's talk about Hawking radiation for a second. I think that this is only the cartoon and not really actually how it works. I have never sat down to read Hawking's papers because I haven't needed to. But the basic idea is, if you've got this event horizon, this is the edge of the black hole in a lot of ways. Inside of this, you have divided by 0, and we have no idea what's going on. So this is the universe dividing by 0, and then you have some region of who knows what. All physics is broken in here. It's all speculative magic inside the black hole. Right at the edge of the black hole, you have a bunch of violent processes. So it's really hot right here, right? And so being really hot means I've got really high energy photons. So I take two photons, I smash them into each other, they make a pion or something, or maybe a proton, or they make something. But things are always made in pairs. So if I have 2 photons and they smash into each other, let me actually draw a diagram. So if I have 2 photons and they smash into each other, they can give me, say, an E plus and an E minus. Those are the wrong ones. That's got to be a zero. Give me an E plus and an E minus. So you always have to conserve how many particles there are. So you make a particle, you have to make its antiparticle. So what if I happen to do this right here, and one of the particles goes that way, and one of the particles goes that way? Then I have a particle that came out of the black hole, effectively. So by this mechanism, this particle is now out here and not in here anymore. This is effectively has left the black hole and can wander off. I don't know if this is actually a real thing. I don't think it's ever been observed. But it's a cool idea. I don't know a ton about it. I'm sure that there's a lot more interesting physics there. So there's all kinds of problems with this because this pileup is so huge that you have all of this stuff in this infinitely thin sheet. Yeah.
So you're saying one goes in and goes out, or one goes out of the black hole?
It doesn't actually leave the black hole. One goes into the black hole. The other one is just outside of the event horizon.
Is it like in the spinning region? Is that what that is?
Yeah, it's in the disk. Now, since I didn't have any mass in the first place, now I have some mass. So that's problematic.
I think I heard an explanation before where they said it was like a gravitational wave effect or something.
Yeah, possibly. Gravitational waves dissipate energy too. So if I have two pulsars, this is the first observational confirmation of general relativity was the Hulse and Taylor pulsar, which is a pair of pulsars that are orbiting each other, and they're emitting gravitational waves as they orbit each other, just like a spinning molecule emits radiation. And they're getting closer together because they're radiating away their gravitational energy, and you can measure that. And they did, and they got a Nobel Prize for that. That was the second Nobel Prize for pulsars. So anyway, less speculative stuff, though still plenty speculative. Star formation in the early universe, and the Webb is looking like maybe star formation is even slower than we thought it should be. I'm going to talk really briefly about the star formation, the main sequence of star-forming galaxies. So this is basically a positive correlation between the star formation rate and the mass in stars, which isn't really what you expect, because really it should be proportional to the mass in gas. But it turns out that it's proportional to the mass in stars. I don't know if this is really the real answer to how stars form, or just an interesting, useful observational analog. But it looks basically like this. So this is here. So the star forming main sequence. This is the star formation as a function of stellar mass of the host galaxy and time in gigayear. So, okay, this is kind of an awful thing. Let's parse this. This is a number with an error minus another number with an error times time. So log of the star formation rate equals A plus B times T times the log of the mass in stars, plus some other number, which is an offset, and it depends on time too. But it's basically the log of the star formation is linear in time. So this is the linear time, goes up with time, has some offset because there's some star formation at t equals 0. So this is called the star formation main sequence, or the main sequence of star forming galaxies. So bigger galaxies form stars faster. And you can see by this that the constant term is 0.8 and the time dependent term is 0.02. So there's not a lot of time dependence. It's weak time dependence. Yeah, that's how I like to think about it. Okay, so that's star formation. and the star formation rate. So star formation rate is slow, regardless of how you measure it. Star formation is inefficient, regardless of how you measure it. So how do we get this to now? So now we want to understand not just star formation, but the evolution and the death. So the birth and the death are tightly correlated, because as soon as you form a massive star, it blows up, it does, and dies. So we want to turn this into understanding what a galaxy looks like by understanding its star formation rate and history, and the recent, and if there's active star formation or not. So all we're going to do is multiply a couple things by a distribution and integrate. But we got to be careful about what we're doing. So I start off with one star. Then I'm going to talk about how, actually, wait, let me write this down. Okay, so I'm going to talk we'll talk about the spectrum of one star. That evolves with time. And metallicity, Z. And then we'll talk about a group of stars. And we're going to call this a single stellar population. This is one population of stars that all get formed at once. So this is everything forms at once at the same time. Then we're going to talk about continuous star formation. And then I'm going to talk about chemistry. I intended to do this in a slide this morning, but I ran out of time because I was trying to write this talk like I did. So here is a bunch of spectra. This is flux in arbitrary units, depending on what telescope I'm using or whatever, versus wavelength. Here we have it in angstrom. This is an O star. This is a B star. This is an A star. This is an F, G, K, M. What do you notice about these different spectra? So what's the difference? So and they're the vertical. So this is higher than this one because it's been shifted up a little bit. They're really kind of all smashed together in the same region, or more so than this, though there is some spread because an O star is bigger. R squared goes up. So there's some vertical offset that's artificial here. Pretend it's real for now, though. So what's the main difference between O and M? Yeah, this one's straight and this one's ratty as hell. What about the slope? And this one is. Yeah. And you can see they go like that. So first off, why do they go like that? What did I say the spectrum of a star is? It's a black body plus an atmosphere. So you think about a star as a black body. What's a black body look like? Black body has the long wavelength tail, a peak, and a long short wavelength tail. No, I said that backwards. Has the short wavelength tail, the peak, and then the long short wavelength and long wavelength tail. This is lambda. It gets bigger going that way. And the peak shifts with temperature of the star. So some of them are over here. Actually, let's look at this window here in the middle. Ignore this line for a second. So this line is on the low wavelength line, whereas this star, you're on the high wavelength above the peak. Does that make sense? So the different regimes of the black body have different slopes, and they depend on the wavelength regime, but more importantly, the temperature of the star. So here we have the same wavelength regime, but we're changing the temperature of the star, and so for the O stars, it's pretty steep and pretty blue. How do I know it's blue? That's a black and white color plot, right? How do I know that that top line is blue? Because there's a lot more short wavelength crap than long wavelength crap. It's really coarse, but that's the basic answer. Whereas this M star is redder because it's got more long wavelength crap relative to the short wavelength crap. So what do we know about spectra? I'm gonna leave that up. I don't think because this is my roadmap. This is where I'm going. I'll leave you up next time because I'm not going to get up there very much further. Okay, so a stellar spectrum is a black body plus an atmosphere. The atmosphere matters because there's stuff in the atmosphere that does all this absorbing. A black body is a smooth curve. None of these guys are smooth curves, are they? But you see more absorption of stuff. Why is that? I'm going to pull up this other slide from a while ago so I can show you how this works again. Pretty sure it's in this one. Yeah, there it is. There you go. All right, so this is the Balmer line. This beautiful teal. This is an absorption feature. So why do I not have, actually let's look at this line. Why do I not have any of this line down here? Temperature's going up. I don't have any of that line down there. So this is a line this is some crap that's in the atmosphere of the star that's absorbing the light from the star. So I have this black body that makes light, and then it's got to go through the atmosphere. Is she laughing?
There's some noise that we can't look at.
Is it a monkey?
Did it erase this stuff?
I can't tell what that noise is. All right. Man, none of the jokes that my squirrel brain presented to me are PC enough to say out loud. Anyway, the squeaky mattress section of GFDI. I'm supposed to keep that one quiet. Okay, so this blue absorption line here, where my thing go? I got this blue absorption line because I've got a hot star. That's what's giving me all of this light. And then I've got some of it gets absorbed by a molecule in the way. So as I increase the temperature, what can I say about this molecule absorbing this stuff? So if the temperature is too low, then the molecule can't get excited, isn't excited enough to do the absorption that it needs to do. So for instance, this is the 2 to 3 transition in hydrogen. So my hydrogen atom has the ground state, first excited state, second excited state, etc. I need to have electrons. So this is an electron here. He needs to be in the second state to be excited in the third state to absorb that photon. So I need to have enough temperature to put that electron up here. So a cool star doesn't have these absorptions. So cooler stars lack some absorption features because they're not hot enough to populate it. A hot star, here's my same, has the electrons completely removed, so it can't do any absorbing in that line either. So if we're talking about this line here, this 3 to 2 transition, if there's no electrons in the bottom step because they've all been ripped off the star, we don't have anything there either. So that's a big part of keep those two processes. Too cold, can't populate. Too hot, can't populate. We have this kind of two-state process. So that's what dictates the star. So that's part of why the absorption features in the O star are so weak, because most of the stuff that would be doing that absorbing, there's not a lot of gas in that lower enough state anymore. It's also real hard for hydrogen to recombine down to the ground state because it's too hot. So that's what this guy looks like. This guy down here, however, has all of these molecules because it's cold, and there's a bunch of molecules and atoms and stuff. Because it's cold, I do have a bunch of stuff in the ground state, and I've got a lot of lines. When I have some metal lines, metal have lots of lines that are really low energy. So we have lots of lines that are low energy that absorb lots of stuff, and you can see that. You can see it in these spectra. You can see this guy peaks here and doesn't have as much radiation here. So you can see both the black body and the atmosphere in this image. So if you look at the top one, you can see the peak is way over to the left. There's not as much red radiation. So you get down to cooler and cooler stars, lower and lower temperature, the black body shifts to longer wavelength, and you can see the whole trend shifts to longer wavelength as well. And you start to pick up a lot more absorption features. I started talking about this without really describing what it is, so which is probably a mistake. These are spectra from stars. So what you do is you take the light from the star and you spread it out over the image. So what you're seeing is the light from the star minus whatever got absorbed from its atmosphere, minus whatever got absorbed from our atmosphere. Usually they correct for that, and I think in this range there isn't a ton. So the atmosphere matters. Now, where am I? Let me talk. Where's? So we need to get these spectra. There's this thing that I haven't read the reading last, but I bet $1 that half of you ask about the 4,000 angstrom break because the book does a terrible job explaining it and just starts talking about the 4,000 angstrom break like you've heard of it. So now I'll explain what it is. So when you're long word of 4,000 angstroms, there's a lot of metal lines that get excited. Calcium has a lot of absorption lines. And in the atmospheres of low mass stars, all of these metal lines do a lot of absorbing. And there happens to be a trend right at 4,000 angstrom. And that's one of the calcium lines, I think, because there's a lot of calcium in the upper atmospheres of these low mass stars. But you can see a huge difference in the spectra. So there's some difference in the spectra to the right of this 4,000 angstrom break. So the rattiness in the spectra still increases as you go down. The tilt still changes, so those are pretty normal. But you notice that even the A and the B stars have a bunch of absorption features south of 4,000 angstroms, but the O stars don't. Why not? Because the O stars are so hot, all the calcium is fully ionized, so it can't do any absorbing. All the metals are fully ionized, so they can't do any absorbing. So this 4,000 angstrom break is important, because if you can't see it, that means there's something that's too bright and it's filling in that wavelength range. And once those really bright things disappear, then you can see the 4,000 angstrom break. This is kind of like trying to listen to a conversation in a crowded theater. So once everybody stops talking, you can hear something quiet going on. But if everybody's cheering and yelling, then you can't hear a quiet conversation. You can't hear your buddy talking. And I think I'm going to stop with the 4,000 angstrom break, because that's where I'm going to stop for the day. Well, no, I'm going to talk about this plot, because this plot's going to show up on the final. So I want you to be familiar with it, so let's talk about it now. This is the evolution of a single stellar population. This is really the important bit. This is like the takeaway of all of the conversation about star formation is this plot. All of this has been gearing up towards this plot. This plot, I take one population of a couple million solar masses, maybe 1,000 solar, I don't remember how many. It's a lot of solar masses, And I let each star evolve on its own. So each spectra evolves as the star dies. So what happens, actually, let's talk about that for a second too. What happens to a stellar spectra? I don't have a good description, but let's talk about the HR diagram for a second, because I got this one. I happen to have this one up. So here's the main sequence. Is this blob right here. It's a line-ish. That's what these guys are. All of these at the beginning. So these are a big population of main sequence stars. Once the hydrogen runs out for the bigger stars, they can't support the burning anymore, and the entropy per baryon goes way up, and they get really large. As they get really large, they cool, and they get red. And they get brighter because they get redder, because they get bigger, because R squared. Because the luminosity is R squared T to the 4th. So they get bigger, they get brighter, they get redder. So they go from here, which is relatively cool and relatively blue, to up here, where they're relatively bright but relatively red. Does that make sense? So that's the first thing that happens. And everything is on that trend. So this first curve is basically the black body of a whole buttload of O stars, because that's what dominates the spectrum. It's all my O stars. They don't live very long. All of this short wavelength light dies. So the number here is the time in mega years. So, or no, in giga years. So this is 10 to the 6 years. So after 10 to the 6 years, we still have a viable stellar population. At 10 to the 7 years, all of the massive stars that were producing this light have died, and we don't have it anymore. That light's gone. And now they move over here to the asymptotic giant branch and the red giant branch. So all of the stars that are giving me this light go over here and give me this infrared light. Then the thing continues to evolve. You can see here is the 4,000 angstrom break. You can see it does. You can't see it here, but by here you can see it. It's kind of visible there. It's definitely visible here. So now you can see that we don't see any of the big O stars anymore, O and B stars anymore. We only see the little stars. And as the population evolves, the whole thing just gets dimmer and redder. But after a certain point, everything that was massive is dead. So after this is the age of the universe, this is only 4 giga years. Over that evolution, there's not a ton of spectral change. Okay, I'm going to stop talking for now. We'll pick up on Thursday. There's nothing to do this week, but there's a reading due next Monday. Read chapter 4. Even if I forget to post it, please read chapter 4 by next Monday. There will be a homework on this stuff that'll be due a week from Wednesday. I haven't posted that yet. I'll post that today or tomorrow. And that's it. Oh, midterm coming up. We'll do the midterm after we do cosmology. So we'll go through cosmology, then we'll have a midterm. I will sit down and figure out how long that should take us. I think I got my notes right here. So I think we're going to finish star formation, do cosmology. I got 4 days. Oh, crap, spring break. Sorry. 4 days on cosmology, then spring break. Then we'll have a midterm the Thursday after spring break. Pretty sure, unless something goes south, it might happen after that, but probably midterm after midterm then. Okay.